Alright, this is the review for our Unit 3 test, which covers 2.5 and 2.6, rational functions, and our nonlinear inequalities. A couple of reminders: I told you if you don't use the step sheet with the 8 steps to graphing the rational function, you'll get 10 bonus points on the test. And this comes directly from our 2.5 notes. Make sure you're able to identify all of these in different rational functions: the numerator, denominator, leading coefficient, and degree of the numerator and denominator. Alright, so question number 1 is asking only for wholes and vertical and horizontal asymptotes. Remember, always see if you can simplify and find a whole first, because if there is a whole, you have to use the new equation you're left with. In this case, there's nothing to simplify, and these are not identical. One's plus and one's minus, so there are no wholes. So we go straight to checking for vertical and horizontal asymptotes. Remember, for vertical asymptotes, you're setting your denominator equal to 0. So my denominator is 2 minus x. So I can subtract the 2 over, but since the x is negative, I'm actually going to add that over and save myself a step. So x is 2 is our vertical asymptote, and it's written as an equation, x equals 2. The horizontal asymptote is found by comparing n and m. Remember, n is the degree of the numerator and m is the degree of the denominator. So in this case, the understood degree here is 1 and same 1. So n and m are both 1. So then on your step sheet I gave you, it has n less than m, n equal to m, or n greater than greater than m, and you use that to determine your horizontal asymptote. So when n is equal to m, you have to do y is equal to a over b, and a and b are your leading coefficients. A is for the numerator and b is for the denominator. Remember, the coefficient is not this 2, even though it's written in front of the x. The coefficient is the number here, which is an understood 1, and here it's an understood negative 1. So a is 1 and b is negative 1, which gives you negative 1. So your horizontal asymptote is y equals negative 1. We're doing the same thing on 2 and 3. So first, determine if there are any wholes. Even if I can factor this, which I can, nothing's going to cancel. The numerator is just an understood 1, so there are no wholes. So for vertical asymptotes, set the denominator equal to 0 and factor to find the zeros. The vertical asymptotes. An x can be factored out. And then this trinomial, this quadratic you're left with here, can be factored. Okay, x squared factors to x and x, and the factors of negative 6 that will add to positive 1 are going to be a positive 3 and a negative 2. Split and solve. Set each factor equal to 0. So we get positive 2 and negative 3, and we have the 0. So we have 3 vertical asymptotes here. Okay, and then horizontal asymptotes compare n and m. So since there is no x term in my numerator, it's like x to the 0 power, because anything to the 0 power is just 1. So my n, my degree, is 0, and m, the highest exponent there, is a 3. So n is definitely less than m, and if you look on your step sheet or you have it memorized, when n is less than m, y equals 0 is your horizontal asymptote. Alright, same process here. Here something does cancel out. X plus 5 is a factor of both the numerator and denominator. So we do have a whole. To figure out where the whole is, you set the reducing factor equal to 0. So the reducing factor, that's what you canceled out. Solve and you get negative 5. Do not tell me the whole is x equals negative 5. The whole needs to be given as an ordered pair. X value is negative 5. We still have to find the y value. So your new equation after that's canceled out is everything that's left. That is what you use to now find the y value of the hole, and that's what you'll use to find the asymptotes as well. Nope, not equations, equation. Alright, so now we plug -5 into that new equation. Alright, so now we're going to calculate and find our y value. So do what's in parentheses first. So we have -5 and -3 is -8, and -5 and -1 is -6. So when we multiply, we do 5 and 8 and 6, which is 240, and you have a negative times a negative times a negative, which is still a negative. Okay, and in your denominator there you have -7. That won't divide evenly, so you can write it as a decimal if you would like, but I would prefer just to leave it as a fraction. But the negative divided by the negative does give you a positive. Okay, so this would be your fraction answer, or that you could say that's approximately 34.29. Okay, so whichever one of those you give me is fine. Alright, now for the vertical asymptotes, denominator equal to 0. We are using the new equation, so the only thing in my denominator is x minus 2. So x equals 2 is my vertical asymptote. Now for the horizontal asymptotes, again you're using your new equation. Identify the degree of the numerator and denominator. There are 3 x's here that are being multiplied. So when it's in factored form, be very careful that you look at the degree as what it would actually be when you multiply those out. So x times x times x would actually be x cubed. So the highest degree is 3. And in the denominator it's just 1. So 3 is definitely greater than 1. So n is greater than m. And when that happens, there is no horizontal asymptote. On 4, you're identifying the vertical and slant asymptotes and then graphing the function. Okay, so again, double check that nothing would cancel out, because that would affect where your vertical asymptotes are. If there was a hole, you'd have to use the new equation. Okay, but here nothing's going to factor or cancel, so there are no holes. So we go straight into finding our vertical asymptotes, just like we did on the last problem, by setting the denominator equal to 0. So you get +1. So go ahead and draw that on your graph. Some of you are forgetting to draw your asymptotes as dotted lines. Okay, so you have a vertical asymptote through the x value of 1. And label that. So this is my vertical asymptote at x equals 1. Now your slant asymptote, you only have a slant asymptote if n minus m is equal to 1. So the n value is 2, and the m value, the degree of the denominator, is 1. 2 minus 1 definitely does equal 1, so we do have a slant asymptote, and you use long or synthetic division to find that. So most of you probably prefer synthetic, so I'll do that. Just be careful when you're listing your coefficients, there's no x term, so you need a 0 placeholder. And then what you're dividing by is x minus 1, so the 0 there would be a +1 that you're going to use. So the -3 drops straight down, times 1 is -3, adding gives you -3, multiplying -3, which gives you a remainder then of -1. When we are doing our polynomial division for slant asymptotes, we don't care about the remainder. This is all we're worried about. You have to know what this represents, though. Remember, this was a squared. This was x squared, x, and your constant. So it drops a degree because we've divided something out. So now this is just x and your constant. So this is -3x minus 3. Pardon the bell. So there's the equation of your slant asymptote. So when you go to draw that, remember this is just a linear function. Your y-intercept is -3, so we'll start at -3, and your slope is -3. So that means you have a rise 3, a run 1. but one of those movements has to be negative. So if you go up 3, you go left 1 to take care of the negative. Or if you go down 3, you can go right 1. Okay, so you get a few points to plot, and you can draw your line through those points. Let me extend mine out a tad. Okay, so there's your vertical asymptote, and it needs to be labeled as well. Alright, so now we have these 4 little sections created by the intersection of those asymptotes, and you need to know where your graph is going to exist. Now normally we would go through all 8 steps to find those points, but since all you had to do here was those 2, to figure out the areas where your curves are going to be, I'm fine with you just using the calculator there. So type in your equation, your numerator in parentheses, so negative 3x squared plus 2 divided by, and then your denominator in parentheses as well. And you can see there's that vertical asymptote is kind of shown as a solid line. The graphing calculator is not going to show the slant asymptote, but we can see that it would run right through here. So our curves are in these 2 acute angled areas created. Okay, so you don't need to worry about plotting actual points and being perfect because it didn't ask you to do all of the other steps. Now you can tell looking at that it does cross the x-axis and come below that relative minimum there. So we are going to cross here. So your curve goes this general shape and then that in that corner. Alright, 5 and 6, I'm asking you to practice all 8 steps going through the entire process for graphing the rational function. So in number 5, you can factor your numerator. So that's what you need to do first so you can see if anything's going to cancel out. Okay, so this does factor out to x minus 2 and x minus 4, which there is a common factor, x minus 4 in the numerator and denominator. So we are going to have a whole. So you set the reducing factor equal to 0 and solve. So the x value of the whole is 4, and your new equation then is just, this was gone, we factored that, it's just x minus 2 over x times x minus 3 squared. So x minus 2 over x times x minus 3 squared. So we plug that 4 in to solve. So 4 minus 2, and then 4 minus 3 squared. So 4 minus 2 is just 2. 4 minus 3 is 1. 1 squared is 1 times 4 is still 4. So that is 1/2. So the y value of the whole is 1/2. So you have a whole. You need to give it as an ordered pair. So it is at 4, 1/2. Alright, and then for your y-intercepts, to find y-intercepts, you're actually finding f of 0. You're plugging 0 into the equation. Remember to use the new equation. So 0 minus 2 in the numerator, and then 0 minus 3 squared. Multiplying by 0 in the denominator is going to give us 0, and you cannot divide by 0. We end up with negative 2 over 0. You can't do that. It's undefined, so there are no y-intercepts. And then to find your x-intercepts, we're going to set the numerator equal to 0. Again, make sure you're using the new equation. So x minus 2 is our numerator. So x equals 2 is our x-intercept. Do not give your intercepts, y or x, as an equation. This is an ordered pair. When y is, sorry, I wrote that wrong. When y is 0, x is 2. So that is the ordered pair for your x-intercept. And you can go ahead and plot that on your graph if you'd like, or you can wait and graph it all at the end. It's up to you. For vertical asymptotes, we're setting the denominator equal to 0. Again, new equation. It's already factored, so we can just split and solve. When you go to get rid of the square by taking the square root, nothing changes because the square root of 0 is still 0. That's just showing this is actually a repeated root, if you remember back to when we did polynomials. So we get x is 3. Now vertical asymptotes and horizontal asymptotes and slant asymptotes are actually written as equations because these are lines. So we have x equals 3 and x equals 0 as vertical asymptotes. I'm going to go ahead and plot what I've found so far. So x equals 0 and x equals 3. And my x-intercept was at 2, 0. Okay, and I had a hole at 4, 1/2. So 4, 1/2. So that would be an open circle there. And actually, I'm going to hang off on that because I think I'm going to need to scale my y-axis. So I'll come back to that one. All right, slant asymptotes. You only have a slant asymptote. Oh, skipping a step. Let's do horizontal. Horizontal asymptotes compare n and m. So in your new equation, this is an understood exponent of 1, so that's just x to the first power. Here you have x to this binomial squared. If I were to FOIL that out, I would have x squared times another x. I have x cubed. So n is less than m. When n is less than m, y is equal to 0. So I'm going to go ahead and put that horizontal asymptote on the x-axis when y is 0. Alright, slant asymptote you only have if n minus m is equal to 1. So you're asking yourself that question. So we said n is 1 and m is 3. That means there is no slant asymptote. Now, step 7, your test interval chart. Choosing what goes on your number line here that represents the x-axis comes from steps 3 and 4. So I have a x-intercept, a 0 at 2, and then I have vertical asymptotes at 0 and 3. So 0, 2, and 3 all go on here. So that creates 1, 2, 3, 4 intervals. And you go left to right. So negative infinity to 0, 0 to 2, 2 to 3, and 3 to positive infinity. Choose any x value you want that falls in that interval. So I'm going to choose negative 1, positive 1, 2.5, and 4. I'm going to save us some time. Actually, I'm going to choose 5 because it comes out. I've already calculated that, so save myself some time. Alright, so when you go, you can just plug this equation into the calculator and come out with these points, and when you do that, you get 0.19, negative 0.25, 0.8, and 0.15. This is why I said hold off, I'm going to have to scale the x-axis or the y-axis because these come out so small. So this is positive, negative, positive, positive. And then don't worry about actually writing the point there unless you really want to. This is the point you are plotting, negative 1, 0.19. And then you can do that for the rest if you'd like. So now I'm going to scale my y-axis. So I have to go down to negative 0.25, and the highest I have to go is half because my hole was at y equals half. None of these are larger than that. So I'm going to scale it actually by tenths. So each is going to be 0.1. So here will be 0.2, 3, 4, 5, 6. And same in the negative direction. So negative 0.2, negative 0.4. Alright, so now I can plot those points and plot my hole. My hole again was at 4.5. So 0.5 is here. So there's my open circle for the hole. Alright, now the other values from the test interval chart. At negative 1, we're at 0.19, so almost 0.2, but not quite. And at 1, we are at negative 2.5. And at 2.5, we're at 8. And then that would actually be at 7. So it'd be just above that here. There's one more unit there. And then at 5, I didn't use 5 because 4 was a whole. So make sure you don't choose the next value that you already have for the whole. So I went to 5, and it was at 0.15. So then you can go ahead and draw those curves of your graph. So you can see we have a point in this corner created by the asymptote. So my curve will be guided by the asymptotes for that end behavior of that curve. And then in between here, we're above the horizontal asymptote, on the horizontal asymptote, and below. So we are actually crossing this horizontal asymptote. And that's not the prettiest curve I've ever seen, but you get the idea. And then both my whole and my point from my test interval chart are in this region created. And that should be a little smoother, but you get the idea. The only thing I'm missing here is the labels that I need for my asymptotes, so make sure you include those. This was my horizontal asymptote at y equals 0. This was my vertical asymptote at x equals 0, and my vertical asymptote at x equals 3. And now my graph has everything that I needed. All of my asymptotes, my wholes, my points from my test interval charts, and the curves. Alright, so for number 6, we're doing the same process, the 8 steps that we need. We can factor out an x squared from the numerator, which is going to leave me with x plus 2. And down here, this is a difference of 2 squares. It can be factored to x plus 2 and x minus 2, because we are subtracting 2 perfect squares. So now we actually do have a common factor of x plus 2. So again, we have a whole. So you set that reducing factor, what you canceled out, equal to 0, and solve to get the x value of your whole. Now you plug that into your new equation. So my new equation here is just the x squared over x minus 2. So when I go to plug in, I have negative 2 squared and negative 2 minus 2. So that's positive 4, and negative 2 minus 2 is negative 4, so that comes out to negative 1. So my whole is at negative 2, negative 1. Alright, the Y-intercept, again, is found plugging 0 into your new equation. So 0 squared over 0 minus 2, 0 divided by anything is 0. This is a Y-intercept. When x was 0, y was 0. Give it to me as an ordered pair. Remember, if you get the origin as a y-intercept, you better get it as the x-intercept as well, or you've made a mistake on one of those. To get the x-intercept, you set the numerator equal to 0. My numerator is x squared. Take the square root, you still have 0. So again, you should have the point 0, 0. For your vertical asymptote, you are setting the denominator of your new equation equal to 0. So that is x minus 2. So you get positive 2. That you leave as an equation. Horizontal asymptotes, we need to identify n and m. So in the new equation, the highest degree of the numerator is 2, and the highest in the denominator is 1. So n is greater than m. When n is greater than m, there is no horizontal asymptote. Okay, now slant asymptote. Does n minus m equal 1? Well, 2 minus 1 does equal 1. So we do have a slant asymptote, even though we had a whole. We had talked about this before. Whenever we had a whole and something was canceling, we had been left with linear functions, but our new equation is not just linear. Our new equation is still a rational function. We still have an x in the numerator and the denominator. So we can, in this case, have a slant asymptote and a whole. So we have to do polynomial division to find that slant asymptote. So the numerator's coefficient here is just 1, and then you're missing an x term and a constant, so you could just use zeros as placeholders. If you're doing synthetic division, this is what it would look like. And then in your denominator, if you were to solve this, set it equal to 0 and solve, you would get positive 2. So 2 times 1 is 2. 2 times 2 is 4. And that's a remainder of 4. So remember, we started out with x squared, so we drop a degree. So this is now my x and my constant. I don't care about the remainder for slant asymptote. So it's the equation y equals 1x, so you just need to write x, plus 2. So then on your number line to create your test interval chart, you look back at steps 3 and 4. So 0 and 2 go on my number line. So 3 intervals for this one. So we're not going to need this extra piece of the table. So negative infinity to 0, 0 to 2, and 2 to infinity. So the x value is your choice. So I'm going to choose negative 1, positive 1, and 3. And again, you can just plug those in individually, or you can type it in your calculator and look at the table. It comes out to negative 0.3 repeating. You can give it to me as 1/3, but in terms of graphing points, most of you prefer it as a decimal, so that's why I'm writing it that way. You get negative 1 and 9 there. So this is negative, negative, positive, and you can write the ordered pairs if you like. All right, so now we have to put everything together here on our graph. Now, I know one of those points that I just got was way up at 9 for the y. So again, I'm going to scale my x-axis slightly. I'll just scale it by 2's, I guess. So 2, 4, 6, 8, 10. Negative 2, 4, 6, 8, 10. The x-axis, I don't have to go very high. I think the farthest I have to go is negative 2 to the left and 3 to the right, so I don't need to scale it. Alright, so I did have a hole. My hole was at negative 2, negative 1. So negative 2 and then negative 1. Now remember, I scaled. This is actually, that would be negative 2, so it's going to be about right here. And then I had a X and Y intercept at the origin. And then I had a vertical asymptote at x is 2. I did not have a horizontal asymptote, and I did have a slant asymptote at the y equals x plus 2. So again, 2 is the Y-intercept, and the slope is just 1. Oh, and actually, because I scaled, I need to be careful. If I go up 1 square, that's actually going up 2. So if I do a rise of 2, I would have to do a run of 2. Or if I do a rise of 1 and then a run of 1. So just be careful with that when you've scaled one axis and not the other. I'm going to stretch that out some. Sticking, sorry. Okay, well, it's not going exactly through those points that it should. Something's messed up. I'm not seeing it shift, but you get the general idea, hopefully. Now we plot the points. Make sure you label those. So I have a slant asymptote, x plus 2, and a vertical asymptote, x equals 2. So the points from the test interval chart were 3, 9, and 1, negative 1, and negative 1, negative 0.3, so just barely below. So you can see our graph is going to exist in these two little areas created by the intersecting asymptotes. So you can draw your curve. Try that again. And you'll have a curve over here. And that's that. All right, now we're on to the nonlinear inequalities. This one is ready to be solved because they've already got the inequality, the function on one side and 0 on the other. So I'm going to go ahead and write what they're asking for here. So this is your function. When is this function greater than or equal to 0? That's asking on what intervals is the function above or on, because of that or equal, the x-axis. Okay, so because of that inequality greater, well, I don't want it solid. Because of that inequality greater than or equal to 0, I want to know where's the graph above the x-axis or on the x-axis. Okay, so to find that I need to find out where my zeros are. Where do I cross the x-axis? So it's already factored for us, so I can split and solve. Set each factor equal to 0, and I get positive 8, and you would add 1, divide by 3. So 1/3 and 8 are what go on the number line. So here's my number line, and it's broken up into intervals by the zeros 8 and 1/3. So then you need to test in each of these 3 intervals created, is the graph positive, negative, and you test for all 3. You can actually do this by hand by picking any number that falls in this interval from negative infinity to 1/3, any number that falls in this interval from 1/3 to 8, and any number that falls in the interval 8 to infinity. And you plug it into that function and see, is it a positive or negative output? You can do that using your calculator as well, or you can just kind of do it in your head. Like pick any number less than 1/3. I'm going to check 0. And I don't even have to write this all out. I can do this in my head, especially when it's factored. It's pretty easy. So when I do this, a 0, 3 times 0 is 0 minus 1. So that gives me a negative. And then in this factor, if I plug in a 0, that's also a negative 8. And when I end up multiplying those, a negative times a negative gives me a positive. So this interval is positive. Here I can pick any number greater than 1/3 but less than 8. So I'm just going to pick a 1. So if I were to plug a 1 in here, that would be 3 minus 1 is 2. That's a positive. And 1 minus 8, that's negative. So a positive times a negative is a negative. So this whole interval is going to be negative. Okay, and any number greater than 8, so if I checked 9, 9 times 3 is going to give me 27 minus 1. That's not going to give me a positive. And here, 9 minus 8 would also be positive. A positive times a positive is a positive. So this interval is above the x-axis, this interval is below, and this interval is above again. And I am crossing at these points. These are my zeros. So these are included. The graph touches the x-axis here. And it says or on, so we need to be sure and include those points with brackets. So on what intervals is it above? So where is it positive? So from negative infinity to 1/3. You can't equal infinity or negative infinity. But we do include this because of that or equal sign. And then we are above, again, from 8 to positive infinity. And again, include 8. You can't include infinity. So for this one, I don't have the function all on one side of the inequality, so I need to move this these two terms over. So I'm going to subtract the 5 over, and I'm going to add the 2x over. I'm doing this all in one step. If you want to do it as 2 separate steps, you can. But notice, these two can be combined because they're constants. The 2x isn't going to be able to be combined with anything. So I end up with 4x squared plus 2x plus 3 is less than or equal to 0, because everything cancels out over there. You're left with 0. So the question is asking on what intervals is the function less than or equal. So that's below and since it has the or equal, or on, the x-axis. That's what we're trying to answer. Alright, so again, we factor, we have our function, and to find the zeros, we set it equal to 0 and factor. So this is going to factor, you have a couple options here. The factors of 4 are 4 and 1 or 2 and 2, so you sometimes just have to guess and check. So if I try 2x and 2x, the only factors of 3 are 3 and 1. Okay, so if I were to do this, this would give me 6x and 2x. That's not going to combine to 2x, so that's not going to work. Okay, I know I have to use 3 and 1 though, so let's try and change these to 4x and 1x. Okay, so if I were to put the 4 here, that would give me 12. I know that's going to be way too high, so let's try the 4 here and the understood 1 here. So that would give me 3x, and that would give me 4x. Still won't get me to 2x. Alright, so it does not look like this is factorable. So we can't factor this. When you have a quadratic that you can't factor, and you had one like this on your homework the other night, and we did one in the notes, you try quadratic formula. Remember, that's x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. The a, b, and c are the coefficients when you're in standard form like this. So the a is the 4, b is 2, and c is 3. Just focus first on what's under the square root, because if you get a negative, we can't take the square root of a negative, and we know there are no x-intercepts then. So let's just focus and see if we get a positive or negative here. So b squared minus 4ac. So 2 squared is 4. 4 times 4. Yes, this is definitely going to come out negative. So we can't do it. There are no x-intercepts. Now, when that happens, that means your graph is not going to cross the x-axis. It is either all going to be above or all going to be below. It never changes from positive to negative. Now, we know we're dealing with a quadratic. A quadratic is a parabola, and when a is positive, that means it's a parabola opening up. So if I have a parabola opening up that never crosses the x-axis, it must be above the x-axis. Because if this vertex was somewhere below, it would eventually cross, because this rises forever. So this is asking, when is the on what intervals, where's the graph below the x-axis? Never. You could say empty set, no solution, never, however you want to say that. Alright, now we get into rational. We have a rational function in our inequality. This one already has the function all on the left and 0 on the right. So we know that this is asking, when is the function, on what intervals is the function less than 0? So that's below the x-axis. And it does not have or equal, so we're not going to include the points when it actually touches the x-axis. Now for a rational function, just be careful. Remember when we did our test interval charts on the rational functions that we just did, you included not only the zeros from step 3, but also the vertical asymptotes from step 4. So for rational functions, when we go to put things on the number line, we have to include zeros and vertical asymptotes. So first I'm going to find my zeros, and you can see nothing cancels out here. So to find your zeros, that's like step 3 in your 8-step process for rational functions. Remember, you are setting the numerator equal to 0. So the numerator is already factored, which makes our life a little easier. Just split and solve, and we end up with -2, and when you add the 3 and divide by 2, you end up with 3/2. And then for vertical asymptotes, then you set the denominator equal to 0. So my denominator also already factored, makes our life easier. Split and solve, you end up with +3 and -1. So we have to put all 4 of these values on our number line and make sure you put them in the correct order. Okay, so -2 is the lowest, and then we have -1, and then we have 3/2, and then we have a +3. Now, if it helps you to identify if it would be included or not if this had an or equal, you could draw the zeros as actual points touching. It actually crosses or touches here. And here's just vertical asymptote, so you could put like a little dotted line. Okay, it's not going to affect this problem because it doesn't have the or equal. But if it did, that's how you would know if that point was included with a bracket or not with a parenthesis. So we have 5 intervals we have to check. Okay, and again, on the last one, number 7, I showed you how to just pick a number and kind of see what it comes out to. So I'm going to do that again. So any number less than -2. Say I chose -3. So I'm going to check -3. So when I check -3, that would give me a negative here. -3 times and minus, that would give me another negative. That would give me a negative. And that would give me a negative. Now, notice these have to be multiplied. A negative times a negative is a positive. And a negative times a negative is a positive. So I end up with a positive divided by a positive, which is a positive. Okay, now I check a point between -1 and -2. So I would check like -half. So if I have -half, this ends up being a positive value. Or I'm sorry, I need to do -1.5. Okay, that still ends up being positive. Multiply by negative, you get a negative. Subtract, still negative. -1.5, that gives me a negative. That gives me a negative. So a negative times a negative in the denominator, I get a positive. But up here, a positive times a negative, I get a negative. And a negative divided by a positive is a negative. All right, check any value between here. Easiest is going to be 0. That gives me a positive. That would give me a negative, negative, positive. Multiplying opposite signs gives you negative. So numerator negative, denominator negative. A negative divided by a negative is a negative. All right, and then I'm going to choose 3 halves. That's 1.5. So between 1.5 and 3, I'm going to choose 2. That would give me 0 here. And this would give me, if I plug in a 2, 4, that would give me a positive. And actually, 0 in the numerator, it doesn't matter what I end up with. Even though I get a negative down here and a positive. 0 divided by anything is going to be 0. Why did I not get a 0 there? That should be a 0. Double check our work over here. So x plus 2. Oh, I just did that wrong in my head. That would not be 0. This is a positive 2. 2 plus 2. This would be 4. That would be a positive. Silly me. All right, so that would be 4 minus 1. That would still be positive. So you end up with a positive in the numerator. And here we said negative and positive. So a positive divided by a negative is going to give me a negative. All right, and then a value greater than 3. So greater than 3 would be, we could check 4. So that would be positive, 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 positive. So positive over a positive is a positive. So now we can answer this question on which of these intervals is the graph below the x-axis. Where is it negative? It's negative on all of these intervals. You cannot simply state, though, -2 to 3, because we are not negative when we are at a vertical asymptote, and we are not negative when we are on the x-axis. So you have to actually list it as 3 separate intervals. So you would say -2 to -1, union -1 to 3 halves, union 3 halves to 3. And you can always type your equation into your calculator and double check and verify what you found. All right, here's another one already set up, ready for us to solve, but it's rational, so we have to do vertical asymptotes and zeros. So vertical asymptotes are set denominator equal to 0. So we need to factor. Factors of 3 are 3 and 1. We want to get a negative 3, but add to a positive 2. So positive 3, negative 1. So you end up with positive 1 and negative 3. And for your X-intercepts, or your zeros, whichever you prefer to call them, you set the numerator equal to 0. So when we go to factor this one, again, we might have to do a little guess and check. We know the only factors of 2 are 2 and 1, so we could have a 4 and 1 or a 2 and 2 here. So if we did 4, that would give me 8 and 1, which would get me to 7. So I actually guessed right the first time. But I do want it to be a negative 7, so I want the 8 to be the negative and the 1 to be the positive. And that would work out, because the negative 2 times 1 could give me negative 2. And that would be negative 8x, and positive 1 would give you negative 7x. So split and solve. So subtract the 1, divide by 4. Alright, so we have these 4 values to put on our number line. So we have negative 3, negative 1/4, 1, and 2. So I'm going to show you this one on the calculator, since some of y'all still want to know how to check the intervals on the calculator. So here, you go to y equals and type in your function. Put the numerator in parentheses. So 4x squared minus 7x minus 2 all over x squared plus 2x minus 3. And make sure you have the entire numerator in parentheses and the entire denominator in parentheses. I need to change my window. Right now it's counting by tenths, so I'm going to change it to count by ones. Alright, so I'm going to go in my table to this interval, less than negative 3. So notice at negative 3 there's an error, because that's a vertical asymptote. So everything less than that, you'll notice all these y values, these are positive. Okay, so this interval is positive. And then between negative 3 and negative 1/4, notice these are negative values. And then between 1/4 and positive 1, it changes there to positive values. And then you can't see between 1 and 2 because it's counting by integers, so you could change your window settings there to tenths. So you can see all the values between 1 and 2. All of those are negative. This is a negative interval. And then all the values greater than 2, they go positive again. So the question is asking when is this function greater than or above the x-axis? And it does not have an or equal, so you don't include any of the points. So we are above when we're positive. So that would be negative infinity to negative 3, negative 1/4 to 1, and 2 to infinity. And that's that.